starting with AM Studio, you will land on this page. Usually you have only the 3 entries for the demo machines. In my case, I have some more. Already worked a lot with it. Basically, AM Studio is divided into 6 steps. So the first step is the selection of the machine, or we call it the selection of the machine profile, as our profiles are a combination of the type and the material. So we're talking about profiles in that respect. You can also load some project if you want. It's also on the stage 1 if you have already a started project and want to continue. The second stage, this is the stage where you just load all your parts, do the orientation stuff, do some scaling or whatever you want. The third stage is there you put the supports, there you attach the supports to the part. The fourth stage, you're able to multiply your parts, do some nesting stuff in a 2D respect. So we're talking about 2-dimensional. And at the stage 5, you're able to do the simulation and also assign the build strategy to the part. And between stage and 5, there will be created the machine file, or the output, as we call it. And then the stage 6, in the viewer, you can have a look on all the laser paths which has been created. And there you can just do some checking on your data. Yeah, so let's directly jump into it. Usually when you start AM Studio, I told you before, you have the 3 demo machines. So the first thing you are doing is you go into the settings and define a new machine by going on the machine tab here. And by clicking on the plus here, you're getting to the add machine dialog. So you're first choosing the manufacturer. So we have quite a lot of manufacturers available here already. I would say for historical reasons, I would just choose an SLM Solutions for this demo. And I will take the SLM 280 as it's one, standard sized, I will say. So I'm just typing in some name, hexagon demo, and sorry, we also add some material to it. This is a really machine vendor specific thing. We are using the material here for reasons of having a typical overhang angle for each material. Maybe I'm not that expert in that respect, but for titanium, let's say there is possible to build up to 43 degrees, and for aluminum, maybe 45 degrees. I'm not sure about it. It's just some random values now from my side, but just to explain for what this is for. So I will stay on aluminum, and then I can enter the build plate height, maybe it's about 20 millimeters. We have the laser count options and the AM lock. If you are interested, I can talk at the end of the presentation about it. What's its zero clamping system we have implemented as well together with Lehmann, with a company called Lehmann. Then you have the possibility to enter a lot of costs stuff. I will jump over it today because it's some really company specific stuff here, I would say. Then you have the build process, so that's our own, that's the Titan core. And in the case of SLM Solutions, we did a first version of Slicer Hatcher that was the basic core. So for SLM Solutions, there are 2 build processes available. Of course, the new one is a lot faster and and thus even can handle the blocked path and such things even better than the old one for sure. So what we have also here are some machine specific values. You can go through them and check them and enter them. And for sure, since the version 2023A, we have also included the simulation. So there's the possibility to do the simulation, to add simulation results or do some calibration on the simulation. There is a PDF attached. There is explained on how you do the calibration for a simulation. So that's a really specific thing. It's about building a job with so-called cantilevers, and then let's cool them down and then cut them off, and they will deform, and you have to measure the deformation. And then you can enter these values into the dialogue we are just showing. It's also explained here on how you get to this dialogue. That's exactly what we are showing here in AIM Studio. So please have a look on the PDF, get familiar with it, and if there are some questions left, maybe you can send me an email and we will deal with it. So basically, we are talking about these two values. So these two values will be calibrated by doing the job I've just mentioned, or what is just mentioned in the PDF. If you have already good working values, you can also enter them here. So it's also possible to reuse calibration values if they are valid for the current machine as well. Yeah, so I will save the profile and close the settings again. Maybe let's stay a few minutes for the settings. What is interesting for a typical customer, there are some directories we are using where the support profile paths will be put in, and the slicer profile paths. And you have also the possibility to buy a CAD interface. So the customer has to buy it, as it's a sub-product we are also buying. So we have to give the royalties one by one. So if the customer has a need of importing steps, or I don't know whatever the native formats are called, I'm not sure. There are a lot of them, STP, STEP, and PRT, and all the native formats, you know. He has to buy the CAD interface to have the possibility to directly import them to AIM Studio. And we have some options here. There is one thing, it's the part collision module. It's a really time-consuming module, so basically, or typically, it should be checked off, because if there is no need that you have to check automatically whether parts are colliding or not, there is no need for that. Yeah, most of the customer can do their jobs without having activated this. So if you need it, just activate it, use it, and afterwards deactivate it again, because it really takes some time. Then you have an overview about the controls. I will tell you when I'm using one of them, because you can't see what I'm pressing on the keyboard. The materials, it's the same story like the machines, just pressing and plus and entering all the values if you want to introduce a new material. There we have some more cost parameters besides the machine. So what's the hardware costs, the personnel, the software, and so you can put all the stuff here, and then you get a better result in your cost estimation then. For the appearance, there is the possibility to switch to a dark theme if you want. It's up to the customer. And yeah, input, there we're dealing with healing as well. So there is usually check the auto check errors and uncheck the automatic healing of the parts, as the customer is able to see which parts have defects and which not. And there is also, for the native import, kind of resolution you can move by just moving the slider here, you can change. And there is some automatic positioning options here. That's the typical or the standard configuration. So if you load a part, it will be then moved and set to a distance to the build plate of 4 millimeters, and the X and Y is as in part, so as you get from the STL information. And the output You can change it at any time. You will be asked when you first start AIM Studio to choose an output path. That's the path where all your machine-specific output, or the build file, as we call it, will land. So yeah, and there are some options for support. Just have a look on it, and if there are any questions, feel free to ask them. Okay, now let's get started, really. So we have created the new one, the SLM280, the hexagon demo here. You can just double-click or start a project, or just moving on the 2 if it's selected. I always use the double-click. So I have already started some different machines, so I will discard the old machine and get the new one I've selected now. So that's the machine, the SLM280, the build plate. So you can here have a look on how it looks like. So let's start. Let's load the few parts. So I have a bunch of demo parts here. I usually take, starting with this one. This one has some errors. That's why I'm using it. So after you have loaded the part, you can see there are a lot of open edges and intersections here. That's what's visualized in cyan and in orange. So the first of all we have to do is to heal this part. So all the intersections and the open edges will be removed then, and you have the possibility to validate the outcome of the healing process. Here, the original mesh and the healed one will be compared to each other, and you get a visualization from green to red, and there you have a scale for the maximum error. And if we have a look at the inner, that's where the error was. There we had removed some triangles here. You can see the healing process did a good job. So he closed the mesh again. So it's just to check whether the corrected mesh is good enough. It's just a check for you whether you have to go back to your CAD environment and do and correct it there, or you can go on with the just corrected one. So it's just, yeah, it's a check, as the name says. Next thing, we are helping our customers to find.
Yeah, just sorry to interrupt. Actually, just one basic doubt. Do we have some demo parts available in the library?
I can send you the parts I'm using today afterwards.
Demo part for practice.
Pardon? Demo part, what?
For practice, like the model which you have imported. So is it also available when we install the software?
Yeah. So this part is not okay for you. So you need another one, or what?
Okay. So are there any other sample part files which are available?
Yeah, I can send you all the parts which are not customer sealed. Let's call it that way.
Okay. Yeah. Okay. Let's continue.
So this one, you can have this one. You can have some other parts here. I have to search for other parts, but most of the parts are sealed for sure, as they are unique, or so it's not possible to share a lot of parts as they are sealed from customer side. Do you need the parts now to do the same on your side, or is it okay if I send it over to you after the?
Yeah, that is okay if you send afterwards. Yeah.
Okay, perfect.
Please continue. Yeah.
Okay, then let's continue. So we help our customers to find a good orientation by introducing the so-called orientation map. So we are just calculating the orientation map for this part, and as you can see on the right side, you get one big map here from red to green areas and some smaller maps here, and I will tell you how this works. So with this little button here, you can move the part around and it turns in all directions. You can see it on the left. And what is this for? As you can imagine, the dark green areas are the best positions and the dark red the worst. So, but how is this map created? You have the possibility to choose 3 out of 5 criteria. So if you open a drop down, there are 2 more. So you can choose 3 out of 5 criteria. So in our case, we have the speed, the build time or speed, yeah, as a criteria. We have the estimated support volume as a criteria, and we have a distortion tendency as a criteria. And these 3 criteria are now divided by 3. So every criteria counts in the same way. And you can change it by moving this weighting triangle to, let's say, I want to just have a look on speed. So as you can see now, the maps are totally identical. And if we are talking about speed, you can imagine if I choose a flat orientation like this, it will be a lot faster than if I have this orientation. And that's for sure. It's because of the count of the layer count. And you know, each layer there is the recoder moving, and the recoder at least takes 7 seconds or something like that. So you can imagine that the build time will increase tremendously. If we have a look on the support volume, if I move 100% into that edge, for sure, now it's a 1-to-1 like this map here. And let's have a look on this. If we go to a dark green area, you can see some small areas here which need support. And if we move red area, you can see big areas. Therefore, a lot more support volume needed if using that rotation. Yeah, and that's how this is working. So the customer chooses 3 criteria he wants to have a look on, and then he can weighten them just to have a look on 1 criteria, or combine 2 of them if you're moving on this line, or just make it equal like it's a pre-selection, and then had a combination of the 3 orientation maps, and in that respect find the best orientation concerning these 3 criteria. And that's one of the recommended orientation. As it's one of the dark areas, there is another one. So do you understand how this is working in principle?
Yeah, so yeah, just Santosh here. So another Santosh Nagaraj. I was just writing a couple of questions. So I'm clear about this step. So just wanted to check, can we give overhang also as a part of criteria for my orientation, or is it under distortion?
The distortion, you mean?
Yeah. So can I give additional criteria, like I want to consider the in the part. Also, I want to consider the Z height when it comes to the best orientation prediction. Can I give those parameters as well?
I'm not sure whether I got the question correct, but you can, if you just want to have the height inside and also the distortion, I would just move it to that direction. So you take only to concern these 2 parameters or these 2 criteria. And if you're moving in some similar colored space, there should be a similar height as well. But it's not possible to save, let's call it that way, to lock in the height and just doing something about the distortion. But as you can see, it's just you can see, so now it's tilting up in that direction. So the height is pretty similar when moving from that minimum to that minimum. You can see on the left.
Understand. So
Yeah.
how does no, since we have not done any analysis, how does this distortion is coming into picture? On what basis it's calculating?
The distortion is just a tendency. So we are having a look on laser paths and laser length in each layer, and also changing areas between layers. But it's only a tendency, it's a prediction. That's not simulation, because the simulation we have, there is an own stage which does the simulation in a calculational way then. So that's a prediction. So, but it really worked out that it's pretty good as prediction.
Okay, so I have a couple of more questions. So one is on build processor you've shown. So is it the software or platform comes along with machine? For example, Renisho, it is Quantum. If it is EOS, it is Print2. So is that called as build processor while selecting the machine?
Yeah, when you're selecting the machine, now we are using the typical output files or the typical print processor. So that defines the kind of file which is created. But in stage 5, you have the possibility to choose the build processor then in detail. But for sure, the outcome of the build processor is machine dependent. So if you're choosing an SLM, you get an SLM file. If you're choosing, let's say, an EOS, you will get a task file, so it's called there. And if you choose a DMG, you will get CLIs and PCX, and it's machine dependent. So you are specifying that the output, let's call it that way. By defining the machine, you are specifying the output. And afterwards, in the stage 5, you're able to do something about the build processor there. Just selecting one and also put all the laser parameters. So we will come to that later.
Clear. So it need not to be on the same machine. So I can just save it in respective file format and export to that particular software. Understand.
Yeah. So it's also possible in AM Studio to switch the machine during a project. So I can also just click here and say change machine, and let's say, I don't know, let's take another one. For example, we have DMG here. Yeah, it doesn't matter. You can choose this one. So now we have a DMG machine. It looks a little bit different.
Got it. The respective build space will be loaded, and respective parameters also. The respective machine build space will be loaded, in the sense all the parameters, right? When we change the machine.
Yeah, the machine-specific stuff is loaded, but all about the build plate, not the build plate, all about the parts, the positioning of the parts, also the supports is saved. The only thing which is not possible is that we also keep the build parameters, as the build parameters are machine-specific. So you have to assign new build parameters then, for sure.
Okay. Understand.
But all the geometrical stuff and support stuff will be transferred, so it's one by one.
Clear. So the last question for now. Calibration strategy in SimuFact Additive, we use a different calibration approach. Just 2 coupon on the middle, and we get the inherent strain values, and we use those for analysis.
Yeah,
I've seen similar calibration approach. So I think we can configure that cantilever position, right?
Yeah, you have to load the cantilever directly here.
Okay.
It's a load, you have the load cantilever here. And then you can move it and position it wherever you want. It's just a guide on how it is. So, but we have one limitation in the, let's say, free version. We have the SimuFact introducing in AM Studio. So we have no, how it's called, we have no isometric calibration. We have only, I don't know what's the word. I have to look it up. I will send you afterwards. So there is some
only
in calibration.
Ortho or iso, like no, is it isotropic or orthotropic? So
yeah,
I think you will have clear.
So we
clear.
have
Just wanted to.
let's call the easier way.
Okay. Okay, understand. Yeah, you can go ahead. Yes.
Okay,
Thanks.
perfect. So if you're not using the orientation map, you can also go to the part option and there do whatever you want, just moving the part on specific positions, turning it around some angles. And what happens in the background, it still has the 4 millimeters at the lowest point because we have you have chosen it here. And if you don't change the set, it will also keep the 4 millimeters also if you're rotating the part. You can also switch between this gizmo or this triad by pressing on E. You go to the rotation gizmo, and by pressing W, you go back to the movement. Also, it also can be switched here, and this just for you as an information. So what you have more on possibilities on moving the part, we have sorry, we have one cool tool. It's called the alignment tool. You can access it by right-click on the part, and there go to tools and to the alignment tools. And what's the alignment tool for? It just selects a triangle and it brings armor to it. And by one click, you can turn this face down to the build plate. So I'm pressing one click here, and now this area is pointing towards the build plate. So you can easily move the part in a very efficient way. If you have some specific areas, maybe you don't want to have a support on it, you can just invert the selection by pressing the shift. Let's say, just for an example, I don't want to have here on this area any kind of support. So maybe I'm just rotating it up and there won't be any support here then. It's just for an example. I've just chosen this area here. So it's an easy way to fast rotate the part towards or against the build plate, whatever you want. So that's what the alignment tool is for. What is more, there are some more tools. We have also the possibility to look into the part. Yeah, it's for sure it's a quite typical approach. You can do it, I think, in nearly software, but for sure you can do it in our case. It's the C for cut. So I can press the C and disable and enable it. The alignment tools, by the way, is pressing the A for alignment. So you can access this tool by just pressing the keys. What is more, we have some really simple measurement tool. As there was no need for some more specific one, you can just, it's just for an estimation, for example, for a diameter or something like that. So you know, this should be, I think that should be 20 millimeters then, or nearly 20 millimeters. So it's just selecting the surface and then measuring the distance between 2 points. It's accessed via pressing the M key. Then we can do a global offsetting. So just make an offset on the part, for example, for 0.1 millimeters. So the whole part get thickened up. I'm not sure whether you could see it. Maybe it was the value was too less. What it does in the background, it also makes a check for errors again, because manipulating the mesh always has a risk of destroying the mesh, the triangle mesh. So maybe you can see it if you have a look on this little face here. So now it's rounded. That's all about the offset we just applied. So you can go back. So now you can see the sharp edges again. So I'm just have undone the global offset. What is the global offset for? For example, for the utilization, I'm not sure whether you know this electrochemical removement of support. So it's a way of just, yeah, kind of bathing the part, and then I don't know the exact chemical process, but it's some kind of electromechanical will remove the support structure then. But for sure also will also remove some layers of the part, and that's why we have introduced the global offsetting, so that the resulting part will look the same after having removed this via the electrochemical operation. So one thing more, I think I have forgotten, it's the labeling. So you also have the possibility on the part. So if you just wanna say Gugu or whatever, then you can choose the whether it's embossed or it's what's engraved. So yeah, so you can engrave it here. Just now we have. Okay, I made it the other way around. So I've not engraved it, I've embossed it. So yeah, now I have a label on it. Important for you to know, the label changes the mesh. That was the reason why you have seen already, again, the check for errors. So it's not the kind of, you can take this and move it around, because it has already changed the mesh here. So you have to be clear where to put it and what's the text of it. Otherwise, you have to go back and create a new label, as it's directly applied on the mesh. Maybe just remove it again. Okay. So in principle, yeah, you can do some scaling for sure. You can, yeah, uniform scale, make it twice, make it doubled if you want. Things for sure. There is one thing I can show you. I think it works with the twice. Just want to show you what this build chamber matching is for. Okay, it's already too small. Still too small. That's the correct one. So recheck. It's not working. Maybe I have to recalculate it. Okay, there is a problem with the build chamber matching. I have to check it with my colleagues. Okay. The build chamber matching basically helps you finding a suitable orientation if the part is pretty big, so there is nearly no positioning possible to fit it into the build plate or the build chamber, let's call it that way. That's what the build chamber helps you through. I will send you some images afterwards. I'm not sure whether this will work. Usually working with the newest version, so that could be the reason that it's broken in this version now. But usually it shows you some gray to black overlay here that you can find the possible positions. So I will remove that part as it was just for the error, and I will introduce some other parts for the next stage, if there are no further questions for the orientation. Otherwise, I would continue to the support stage then. Okay, then let's go on to the support stage. The next one. Let's assume that are the correct positions and orientations for every part. Now we are in the support stage. Let's have a look on the support stage. In the support stage, usually only the selected part is displayed. That's for visual reasons, so you can better have a look on the support regions, so you can see them skimmering through. And if you have on below, from the downside, you can see also some coloring about representing the angle. So what we can do here with this example, it's a dental bridge. In the dental market, they are just using the rods. They are not using many different kinds of supports, but I want to show you some really cool stuff we are able to do with the rod support, and we call it sampler. And the sampler is working that way that you can choose out of 4 different samplers. It's the midpoint sampler. It just puts 1 pin below the lowest part for each region. Then we have the contour sampler, and also the other 3. These 3 are combined in one infographic. So the regular grid just puts in a grid shape rods, in a rectangular way. The Poisson disk sampler just introduces some randomness to the positioning of the rods, and the contour sampler just follows the contours on both sides and makes some rods there. And I will show you one by one what's happening here. At this point, please always have a look on this little icons here. I like them really well, and it helps you a lot getting into a studio in a quick way, as you can always see live some infographics. And I'm a visual guy, so it helps me a lot not to have a look every time in the manual and then just have a look on these icons. So let's start with the midpoint sampler. If I just generate it, you can see it's done for all regions available. Just putting 1 pin at the lowest points per region. For sure, it's not enough as support. So I will also introduce the regular grid. I can just combine them and press regenerate, and now I get some. You can see it here, some rectangular shaped rods here. But if you can also see that there are a lot of areas where there could be some need for further rods. So I also will add the Poisson disk sampler. And if I regenerate it, you can see now I get the good coverage of all areas. And yeah, you could print the part as it is now. So we have combined this 3 sampler in one profile. So basically in AM Studio, you are able to work with support profiles. So we have a lot of, not a lot, but some of them already shipped with AM Studio. So you can choose out of a few pre-selections, and you can just save everything you do in the support stage or with your support types to a new profile, and you can reuse it as you like. So what's more about the rod sampler, you can choose different shapes here. You can also create solid if you want solid pins. So we just can have, just for an example, I'm choosing the pre-selection, the rod solid single. It's quite the big one, and you have also the possibility to just putting 1 pin to the mouse pointer. So now I'm pointing here, and if I'm pressing the key P, 1 big rod here, and in that case it's a solid one. So it's also closed. Trying to get rid of this single one. I think it's not that easy to fetch it. Sure. It's gone. Just for you as an example that we can also use the solid pins here. So that's the first type of support we're using here. For example, in the dental. Let's go on with this part. You have maybe seen that just after having selected it, the regions are already calculated and will be colored depending on their angle. So let's go through this part, and let's start with simple block support. So just selecting the region I want to apply a support to. And there you can see some block support specifics. So on the one hand, it's a tooth pattern. So we have the teeth bottom and on the top. That's this tooth-shaped way of connection between build plate and support, and also support and part. We have the perforation. Again, the infographics. It's all about this little diamonds and the walls. We have the fracturing, also explained in the infographics. So that's the cut off of the grids in some specific ways. So we have a 3x3 area defined, and after the 3x3 crosses, there is on each side a little cut in here. So you can define everything you want here. If you want to combine two or more supports, you can do that. So as I have this selected or applied already the block support here, I could also introduce the last of our sampler. It's called the rod contour. What's the difference? It's now the contour sampler. As I showed you before, it's just following the contours. And if I apply that to this area, you can see now you have on the edge, following the edge, you have the rods again here. Combined the two different support structures here. If there is some need to get more stiffness. Okay, let's move on to this area, and I will introduce the next type of support. It's the so-called adaptive cell support. And as the name tells us, you can see it's working with so-called cells. Maybe you can see it here, some quadratic, some shape of cubes. So we're working with cubes here. We've got small cubes at the top, and then increasing the size to some medium size and some big, large size. So what's the benefit of using this support? You can spare a lot of powder. You can also increase the speed, as there are fewer laser paths than having a block support from the top to the build plate. What's more, this is a good support for the heatization I've mentioned before. So even the liquid can go easily in there and also remove it at the top. And you're not only saving powder by using less of them, it's also easier to fall off because of the structure. So the powder which is also in there will be more loose and even easier fall off the part, and so you can reuse it in some kinds of machines. You can reuse the powder you're not using. For sure, this support type needs at least a little bit of height. Otherwise, you can't enlarge the cubes. So you need at least some. I would say. It depends. It depends on how you have defined the structure here. But for sure, it has some. There is a need of a minimum of height so that cells could work out their potential. Okay, what we have more, if we take this one, I can show you one nice feature. It's called the deformation. Just activate the deformation here. So there we get the visual with two arrows and one area. And you can move it there, and then it makes some kind of knee if you need it, and you can move two arrows. You can change the shape of it as you want. And there is also a possibility to do it the other way. You can use the gusset to apply that. The gusset is a fully direct support, so in that way you can see it angles directly towards the position I've chosen. And with this, you can also do something like this one, building some kind of balcony. A little more here. if you want. So it's all possible. Okay, so that part is not fully supported yet, but yeah, doesn't matter at all. So let's continue with this part. There I can show you the last two possibilities of applying supports, the last two types of support. The first one is the tree support. Let's have a look on the tree support. Yeah, as the name says, it's building some tree-shaped support. So I will just enable one thing. So if we just press generate on every region, you can see there are built a lot of trees and they have different shapes, some of them pointing to the build plate, some of them pointing to the part. So it's kind of mixed. And again, the tree support is also working with the sampler. So all the connection points here are just using the same sampler as the rod support. So you can define by using the sampler on how the attachment from the support to the part. What I want to show you is if you changing the pre-selected profile for the supports to, let's say, the tree to platform. I will just remove the already built ones. Sorry, just remove them. You can do all the stuff over the tree here as well. And if you now create the tree to platform, you can see most of the stems are now pointing to the build plate. Even some complicated ones like this one, you can see it just angles away from the part and then go directly to the build plate without touching the part at any point. So if it's possible, here it is not possible because there is no way of getting besides that structure. But everywhere it's possible, the tree support finds its way towards the build plate without touching the part itself. So it's a really cool way of supporting some areas which are hard to connect to, but for sure at the price of stability in XY movement, for sure. So it's not that stable as a block support. Yeah, I think that's obvious. Okay, and last but not least, we have the line support. So I have to search for a line. Here it is. So here we have a line or an edge. So you can just put a line support underneath. It's just a single wall with so-called struts that are the 90 degrees triangle-shaped support structures combined with that, just to have a good connection. Oh, sorry, lost my edge. So that's the way how this is working. For sure, you have there a lot of options available. You can remove the struts, for example. Then you get just the wall. And as we know, that's not enough. So there is one cool thing I want to introduce you as well. It's the line thickening option. And if you enable the line thickening, therefore you will get a block support which surrounds, let's call it that way, which surrounds the edge. So now we have the line support on the edge directly and the block support besides the edge. So it's a really cool way of supporting some edges here. And it's done by the line thickening option. Yeah, for sure. There is much more to explain about the structures, but as an introduction or just a way on how it's working, I think I'm through this stage. So I'm open to questions about the support.
Yeah, Santosh here. Okay, so it was echoing. So couple of questions on support. So sometimes we try to use solid plus shell support on the same surface. So do we need to create a different category and generate that? How do we do it? For the same surface, in the middle, we need a solid support, and the rest we may require a shell. So I think we can use the line one, which you have shown just now.
Mhm. Yeah, now it's only possible to use solid support in the rod. We have only rod support as a solid now, but it's planned to have, let's say, some thickened up block support on the roadmap as well. But it's not possible to let's say even select the region and just just extrude it to the surface as a solid. That's not possible yet. But we are
And
still,
if I have support generated in any CAD tool, I hope we can import that, right?
yeah, for
So
sure.
let's say
If you have done the support in a different program, or I don't know, if the positioning is correct, you can just load both the part and the solid, let's call it that way, and then it's shown as two parts here in the tree, but nevertheless it's able to build. So
okay,
you can,
so if I cannot select the surface, is there any option to avoid internal support where I will not have access to remove those supports?
for sure.
Okay.
If you're using external support, you don't have the options to manipulate, because then it's interpreted like a mesh, like
Okay.
like an STL. So you can only manipulate or update or edit existing supports if you're using AM Studio ones, for sure.
Clear. And how do we define this a different parameter? Is it coming in the next tabs? Different printing parameters to the solid support and shell support, or if you want to define
parameter will come at stage 5.
Okay. Clear.
So
The last question again.
Yeah,
Yeah, that is clear. So I will wait for the build parameter. So do we have option to number the parts? For example, if I'm printing 10 parts, as you shown, how do we label it? Can we have the option to label it like one by when I have nesting and number of parts?
the automatic labeling is not supported yet. So you have to put the labels on your own.
Okay, I think that should be. Okay, then I'm done. Thanks.
Yeah, that's a question we get quite a lot for parameter studies. They want to have it that way. But to be honest, it's really difficult. It's not difficult, but at the end, I don't know how to tell you, but it's a big benefit for powder development and for maybe some manufacturers, but not for us in principle. So it's very difficult to plan such a feature which we won't have any revenue on our side. So it's a really specific one if you do parameter studies and so on. And we got questions from many universities if we can do that, but they won't pay for it. So it's quite difficult for us to introduce features where there is no revenue. I think it's self-explaining.
Yeah, I understand.
Such features are prioritized pretty low then. But for sure, we have thought about it because it would be a nice feature to have some automatic labeling. But also then you have to take into account the shape, and also if it's possible, if it's just a nesting, if it's just a copy, it could be, in my opinion, quite easy. But if you want to do some automatic enumeration of different parts, it would be a little bit tricky to find the correct space where to put the label, or just adding some feature where you can put the label on it. So there are different approaches, but no time for that.
Clear. Okay, thanks.
Yeah. Okay, let's move on then. I will just remove it one part that we can that we can go a little bit faster through the next stage, as there is no need for them. So the next stage is the nesting. So we have basically two options to do some nesting. I'm just moving the parts a little bit around so we can see it a little bit better. On the one hand, you can do it manually by just selecting on how many parts you want from each, and just putting some distance between, and then you press arrange, and then you get, yeah, I've just moved over the border, so the parts got red. Now we have the original part here, and because we did the manual nesting, we get this chain symbol, and this tells us that there are instances. In our respect, instances, you can see that the tree here as an additional entry under the main part, so you won't find them in the lowest hierarchy, or in the highest one here. So they are connected to the original part. So if you're just doing anything on the original part, like rotating a little bit, all the other parts will be rotated then as well, because they are connected. So that's what we call an instance. You have the possibility to remove this lock by just convert to part. Now you can see an additional copy here, and one license less than before. So we have only the connection from these two instances to this part. This one is independent now. So what happens with the support? Maybe you are wondering what's happening here. As we have some gas flow concerning parameters in the support, there is a need of recalculation of the part of the supports if you're rotating the part. So that means if we have a look from the bottom, you can see the support is still parallel, even if the part above has another rotation. So that's kind of gas flow specific or recode aligned support, or not aligned, just rotated about, I would say, 15 degrees or 10 degrees, I'm not sure. And to be sure that this also is the case for the rotated part, the support has to be recalculated if you rotate the part. Yeah, I think that's all about the manual stuff. I will just delete the parts again. And yeah, let's have a look on the automatic nesting. There we have two options. The one is just to tell the genetic algorithm on how many parts you want to have, or just say, okay, I want to fill the platform with a compactness. So that means how many parts we want, or no, the percentage of how many percent will be filled up from the build plate by trying to get the parts placed there. So we can allow the Z rotation or not. That means if you disallow the Z orientation, we can work with instances again. So it's just a really identical copy of the part. If we allow the algorithm to do some rotations as well, you will get copies of the part, just to keep in mind on what you're working with. So I will disable the Z rotation so I can work with instances, and I will just increase the compactness to 60%. And we make a quick try so that we won't have to to wait a long period, just pressing arrange, and let's have a look whether the genetic algorithm is successful or not. So he does only 3 iterations now. Let's have a look on the outcome. So he tells me in this short period, I would say it was about 10 seconds, he had no chance to find a suitable solution. But if we have a look from above, it's not that big deal. I would just move some parts a little bit into the inner, and then it works out. So you can see now you can already print it. So there is one gap here. Yeah, it's because of the 60% and because I just made a quick try. So there was not enough time for the algorithm to find the correct solution. But you can use a normal fit or a best fit, then there will be a lot more time consumed by finding a suitable solution. Okay, if you're finished with nesting, you go to build process. I had a feeling about that some of you are still waiting or really waiting for this stage, as there were some questions about the build parameters already. The stage 5 is divided into two parts. The one is the simulation and the other one is the one requested. It's the selection of build parameters, the assignment of build parameters, and do all the things which could be changed or could be manipulated for the for the creation of the build file. Then, so maybe I will finish up the, let's say, usual way of working with AM Studio, and I will deal with the simulation separately, if it's okay for you, because the simulation itself is a topic which there could be a need for a customer or not. So some customers like to do the simulation, others say no, there is no need for that. So I will just finish the steps without simulation, then I will come back for the simulation topics. So let's say that's our build plate. We have a lot of instances here. That's pretty good. I will tell you why. Because an instance, there is no need to do the slicing hatching twice. If you have done the slicing hatching for the original part, you can just offset or copy the results for the instance. So it's sufficient to do the slicing and hatching twice in that case, one for the anti-cron and one for the Maschinenbautile. And the other are just copies. You can see when I press slice hatch and how fast this could be done. What we can do here is we have, again, some profile management here. Build profile, you can select the build profile. Maybe you have some specific ones available. You can change in the slicing some scaling. That's about the size reduction when the cooling takes place. And you can enter the slice thickness, and the height factor just defines where the laser is focused on in this line. You can also do some filtering if you want. There are a lot of, again, some infographics, and feel free to have a look on it. As well, you can choose a sort strategy for the support. And you can also use a filter for the support, or do a skipping layer if you want. You can use only every second layer for the support, in comparison to the part where you put energy to every layer. What is more, you can do some specific hatching. You can change the volume. For sure, you can change the way of how is hatching being done. There is one interesting one we have introduced with the last release. It's the lattice structure, so you can hatch with some kind of lattice structure. You can define how the border look like. You can deal with block path. You can also do just a fill contour if you want. You can specify some hatch pattern dependent values. Hatch offset, hatch distance, stripe offset, stripe length. You can do the merge if you want. You can do some alternating between the layers. You can apply rotation. I'll also show you. We can apply rotation on each layer if you want. There is a lot of specification possible for the hatch process if we are allowed to use our own slicer hatcher. That means we have only the possibility to change anything, let's call it that way. I'm not sure whether it's all, but let's say anything depending or concerning the build strategy, if we are allowed to write the machine-specific data on ourselves. So if we are pushed to use an API, like we have it with EOS or Trump, there is no possibility of changing the values in that detailed way as we have the possibility, for example, for DMG, E+3D, or SLM solutions. So it depends on the cooperation with the machine vendor on how much we can manipulate or edit the build parameters. What is more, you can also change the order of scanning. What that means, which laser laser path type will be done first, and which then, and so on. And you can even change the speed, power, and focus for every of the types, of the vector types. Yeah. So there are a lot of possibilities here. If you are using the Titan core, that means the CAD additive slicer hatcher, the performant way of doing slicing hatching, let's call it that way. So you just select a part and then choose whatever you want, and then assign, and then you get the build strategy assigned to the part. And as we are working with instances here, for every instance, it's automatically overtaken. It's using the same build strategy as the main part for sure. So we have here a 60 parameter, so we should also change this one to a slicing of 60. So that you know the problem when using different build strategies with different heights of slicing, I assume. Is it clear to you why it's recommended to at least use some slice thicknesses which fit to each other?
No, one question, Aishan.
Yeah.
On slice thickness, we are clear, like 60 micron we are defining. What is slice height factor? 0.5?
This is just where the focus of the laser will be pointed at. So the 0.5 means that when we have 16 microns, the first layer will be energized at 13 microns then in the middle of the layer. It just specifies where the laser is focusing within the layer. If it's in the middle of the layer or it's at the bottom of the layer, that makes some difference. I think EOS is working differently. You know what I mean? That's the position, the set position where the laser focuses when energizing the layer.
Okay, clear. So most of the time it is on the middle?
Yeah, the 0.5 is the middle, it's the standard.
Okay, clear. Yeah.
So it's possible to, for sure, it's possible to to assign different build strategies to different parts. For sure, the instances get the same build params as the original part. That's I would say that's the advantage of using instance, and for sure also the disadvantage. If you want to use different strategies, then you have to convert to single parts again. You can also define sections. A section is a how to call this, a split within the part in some specific set height. So maybe I will just load in another part for this small. Let's take this one here. I'll just move it here. I'm just doing some quick stuff for you to show. So there should be some healing here. I'm just putting some simple, stupid support on it. Just generate, yeah. And this, I will show you what the section does. So I will make the other parts invisible so I can see it a little bit better. By right click and define sections, there is opening a new sorry, a new dialog, and there you can define sections. So that's a kind of cutting the part into parts, and therefore you can select for every section a different build strategy. So let's say if we just selecting the first one, just trying to select the upper one. Here you can then select different strategy. Maybe I have a 30, no, I have a 30 micron here, 50 micron. Maybe I'm choosing the demo and then I'm just switching to 30. Say assign. Yeah, now it should be this one. Assign. Yeah, let's have a look on how it looks, how it turns out. So hopefully this I have done it correctly. I'm not using that so much, to be honest. Okay, let's have a look on the outcome, I would say. So I have assigned my build strategies. I have moved and supported all my parts, the other way around for sure. And I'm using our internal slicer hatcher, and I'm now just pressing on generate build. So he tells me that I haven't saved the project yet. So I will save the project. One demo. So as I told you, I had already one or twice, not one or two. So I'm saving. And now that's the thing with the output directory. I told you that you can define an output directory where all the output lands, and you will be asked every time you creating such things. I leave it the way it is, but I don't want to use it always, so I won't check this. So this dialog will show up every time I press on generate, but for me it's okay. So I'm pressing on generate, and now our slicer hatcher is working. And as you could see, it's a really quick one. And what is more, it also works that good because we were using instances. Otherwise, the slicer hatcher had to calculate every single part, and now we have only 3 parts to be calculated, and the others are copies. So that's the main advantage of using instances. Again, I think it's worth to mention it again. Yeah, then you can go through the slices, and as you chosen 30 microns for the tube here, and that's the reason why every second layer I just see only this. For sure, you can see. So that's the reason, because we are now in the lower section, and if I go up, I use the normal. I think it's too high. I've chosen for both sections, I think. Sorry, I've selected for both sections. But for you, just as a proof of principle, so here we have the 30 microns, so we have on every layer. Oh no, I test a different one now. Cool. So I managed to yeah, there was the difference. Could you see? It's the 50 and the 60. That was the problem. I've chosen the 50 and the 60, and so we have every fifth layer, we have both of them. And besides that, we have on the one hand the tube, and on the other hand all the other parts, because the slice thickness does not match that good. That was the problem I mentioned before. So I think I made a mistake in configuring this stuff. So now we are on 750, and now in 760. There are only 10 microns between, so that's not good. Now we have 40 microns, as we are on the 41.8 with this one again, and then the 20. So these parts are moving in 60 micron steps and the other in 50 micron steps, and that's why this is not working that good. But now the next one, here we have all again, because it's the fifth. Every fifth time we have all together in one slice. I don't know whether it's clear or not. Sorry for going too much into detail. What we can also see here, you can remove the arrows. Then it's a little bit faster here, because there is every line, there you can see the line pattern, the stripe pattern, and you can move through the part to see on how it's built up. See, there's the offset contour, the second one, and now the border at last. So you can see on how this is, or not on how it will be energized in which direction. So we're starting with the hatch, then the hatch offset, the contour, and the support is last. That's what we see with the coloring of the bottom line here as well. So what we can do here more is we can have a look on the graph. Now the graph is being calculated, so it's calculates the layer times for each layer. There is a need of time on how much the layer will be energized, and also the recoater. This is also put together with to this value, and we get some graph on the right here. It will show up in a few seconds. Here you can see, and that's the time which is consumed by the layer of the machine. So if we go to this peak, so I try to exact peak here, just to have a look why we have this here. Maybe we can see, yeah. You can see there is one peak, and if you go there, you see the upskin, and the upskin is just a second. So that the layer is lasered twice, and that's why we have a lot more time for this layer. And so you can use the graph to see what's happening during the build process, if there are some jumps within. So you can also imagine the more time you take for the layer, the more energy is brought into the layer. You want to have a smooth shape of this curve, so there should be similar energy entries per layer. So we try to omit such peaks, maybe by just rotating the part a little bit into X or Y, so that we can get rid of such big areas. Be energized at once in one layer. Yeah. And what's more, last but not least, we can do the build estimation, the cost estimation, cost estimator. And therefore, we get the price for the part divided in every value we have written down or defined in the settings I showed you in the beginning of the meeting. So you can see a lot of stuff, and even some build time estimation, and yeah, general information. So in principle, that's the the straight through way of using AIM Studio. As I have promised, I will tell you something about the simulation as well. But before we start with the simulation part, are there any questions?
Yeah, a couple of questions. Section, is it only to the part? If we have multiple lasers, can we play with no overlap area and other settings can be controlled over here, or is it on the machine?
It depends on the manufacturer again. For SLM, the laser selection is done by the machine itself. So we had no chance to do it on our side. In principle, we are prepared for that.
Okay.
As you can see, if I go to this scanning, there you can choose an index. So in principle, we could change or assign a specific laser to a specific type of build laser index. No, sorry, to a specific
CAD
vector
strategy.
type. Yeah.
Okay. Yeah.
But it depends on the manufacturer because there is a lot of multi-laser alignment or assignment done by know-how by the vendors, and they don't even like to show to us. And we have also some manufacturers which say, yeah, please do some laser arrangement for us. You can do it. So that's one thing I would say it's still in development. So there are a lot of machines who can do this by their side, but on our side it's currently under development because we just get in touch with one machine vendor where we are allowed to do that. So that's basically it's a quite new topic for us. So we are developing this now for the specific vendor.
So during cost estimation, so can we also estimate for individual parts, or is it a total cost estimation?
If you want to have it only for a few parts, you have to put only a few parts there. So it's a cost estimation for the whole build plate. And also the cost estimation is machine dependent. For SLM, for example, we have integrated their build time estimation. So we were allowed to use the same which is on the machine. So we get exactly the correct values also for multi-laser systems. For other vendors where we do not get access to the build time estimation, it is calculated then as a single laser, even if it's a multi-laser. So you have to maybe reduce the time dividing by 2 if you have 2 lasers, if there is only a small overlap.
Yes. And
So
there's another report generation. Can we generate a report out of it? So need not to be only cost estimation report, overall report on.
You can export it to a CSV, so you can open it in Excel then and have a look on it.
Okay, will it also include a strategy used for a particular part? So what is the layer thickness and all this info?
No, I don't think so. There is a connection to it. We thought about having a, let's say, print report. But to be honest, there were less demands for that as we first assumed. So we thought about it to have a really good, an overview over the print job, let's call it that way. So what were the parts, how long they take, which parameters were used and such stuff. But as it is, all this data is saved in the project file, there was no specific need or let's say not that many needs for that it has ranked higher in our priority list.
Okay, clear. Thanks.
Okay, if there are no further questions, I'm sure there will arise a few questions in the future for sure. Feel free to contact me via email or just give me a call or something like that. I would propose to go further with the simulation. So I will show you some simulation stuff. Maybe that reason I will create a new project to speed it up a little bit. Just take this one. It's just flushing all of the data out of it. So that was the reason for the restart. Okay, I'm just thinking of a part where it's easy to see. Okay. So we do some simple, stupid supports. Maybe I'm taking the part a little bit, so there is no need of that much support then. Just putting everywhere is block support because it doesn't matter at all. It's just to have some support. And then we go to the simulation, so we can simulate the part. Just take some time. And first of all, before we can start the simulation, we have to do a calibration firsthand, but I do not have a calibration as I have no real machine. You have to create the voxel mesh. The voxel mesh is just a cubic way of representing the part. So there will be some cubic grid matrix, three-dimensional, laid over the part and the support. And therefore I can choose the voxel size and all the stuff here. So I leave it as it is, and just creating the voxel mesh. So you can see what does that mean. So hopefully the part is not too big, too struggling with performance, but I think it should work out nice. Okay, it's quite. It's too big. Yeah, let's have a look. The voxel mesh at least. Maybe I should have increased the voxel size a little bit for demonstration. As you know, a simulation can take a lot of time. So what happened? You get a lot of these small cubes here. And regarding the color, that means that the deep purple ones are fully or at least mostly full in the part itself. And the brighter they get, the lower percentage of part is within this voxel. So that's why this coloring comes from. And there is some visual stuff here, some flickering. So if you have the voxel, then you can start the simulation. So I get the message about the calibration, so I have no calibration, just pressing OK. Hopefully the simulation is working out fast. Just having a look when it starts, then we can make some prediction on how long it takes. Maybe I've chosen a really big part. Yeah, it should work out. Maybe we use the time when we're waiting for the simulation result for some further questions. Maybe there is one or two coming to your mind. If not, maybe I'm just talking about what we have already, how to say, what from our point of view are possible reasons for doing some simulation stuff. Yeah, for sure. If you have a demand of printed first time, right? That means you have a customer which has, yeah, maybe some big part or some really specific part which is very expensive to produce, then maybe you don't have the chance to try it 4 or 5 times because it would then the bill would explode. So therefore, it could be a need to do a really exact simulation for the part first and then correct it and then print it. The second thing we have recognized is that even if you're using some big size voxels, let's say do some low precise simulation, it can help you to find where maybe a support is missing, or maybe even you can see some deformation tendency there as well. If you see something like that, you can even go more into detail and lower the voxel size so that the simulation result will get more precise, and you can do a better pre-deformation then. So I would say in principle that are the two of the most important things we see on our side for having a simulated part. I think please.
It uses SimuFact additive, right, for meshing and analysis.
Yeah.
So analysis will be done with SimuFact additive. Right?
Yeah, for sure. You can see it here. So the simulation
So we
is completely done by SimuFact additive. We are concentrating on the representation and on the on the integration of the simulation part of SimuFact additive to our product.
We are familiar with additive. I think this one looks like we have limited course availability. So otherwise, it should.
Yeah, we have only support for a single core, so that's the reason why it takes so long. And yeah, all the stuff here. So it did when using SimuFact, as it's a very expensive tool and a very cool tool, and you can do a lot of things with SimuFact additive. So let's say we get the basic version, let's call it that way. So we can do a simulation on one core. In future, customers should be able to buy another core or another 3 cores, so they could use 2 or 4 cores at least. And also they will get if they want to have, they have to buy for it the platform remove, the platform cutoff and the support removal stage as well. So we don't have this one in the basic version, which is integrated in AIM Studio. So
okay. So really it is only build simulation as of now.
Yeah. That's only as built. Let's say the first stage, and only 1 core. That's its standard included. That's where a customer has not to buy anything. But if he wants more, he has to put in some coins. For sure, as SimuFact additive itself is a very powerful and very expensive tool. But we are glad that we could integrate this basic version of SimuFact additive, let's say for free, so that customers can get in touch with simulation as well. So I think it's pretty cool integration here. But I see now that I've chosen a too big part for this one. So we have 2 possibilities: still waiting for it, or just killing it and loading a smaller part. It's up to you. If you say you are very familiar with simulation, we could also cut off.
We can go ahead with small part because we work with SimuFact every day. So
Yeah.
And then
So I will just.
We just wanted to know the integration, like how we can.
Yeah, for sure.
We can go with a small part as well.
Yeah, I thought it could handle this one, but I think with one core, it's a little.
Oh no, one core, no. It's it is sufficient for only GUI, not for any analysis.
So I take even a small machine now and just take a little. Yeah, I don't know. Maybe yeah, I don't want to take the cube because the cube is really silly, I would say. Maybe I can use the arc. It's a small one as well. Okay. So I'm putting some support on it. Calculate. Just putting some support underneath. Going back to build process, voxel mesh. I even increase it a little bit so it will run a little bit faster than. Oh, I just started the nightly. Okay, that's a version which isn't ready for you at this point. Yeah, but maybe at an out. Well, what's the word? Ausblick. As a view in the future, it will be handled different, like now. So I'm just having a look on what happens if I start the simulation now. I've chosen the wrong version. I've chosen the nightly, so the really newest build. So we have also some voxel information here. It won't be available at the 2023 C version, but it will be in a future version. So it's kind of preview. You are the delighted ones of having some preview. So that's the outcome of the simulation. So you can see where the distortion is the most. And yeah, you can also put some deformation on it. So now we have, this is the original part. And if we do some deformation, so it's the other way around. So it's explained in this infographic. So that means if you want to deform the part in a way that you can, that the part which will become which comes out if after the cooling down and all the stuff and it's correct, you have to deform the part in the other way around. That's why the minus comes here. So for every voxel, for every distortion calculated, you will apply the opposite way of the deformation, so it will come out correctly afterwards. So if I press on the apply button here, you maybe can see a little of, can you see it? It now turns a little to the middle as it is pre-deformed, the other way around.
More like a pre-compensation, like bending in opposite direction.
The pre-deformation, yeah, we call it pre-deformation in our program. But yeah, that's exactly what's done here. So we try to pre-deform the part that it will be printed as intended, or it will come out as intended. So yeah. So what are future steps planned for the simulation on our side? Because for now, that's principle all. You could change of which we will be shown. Here it's the overall distortion in the sum of every direction. You could choose then the X, Y, and Z separately. And also you can see the simulation on the mesh, on the 3D mesh, and not only on the voxels. And for sure you can even go through the layers as well as you are used to seeing in SimuFact Additive. So there are steps coming up, and for sure also these two different scopes, I would say, will also be introduced for sure. That's in principle the integration of the simulation.